Greetings, welcome to this new video about Norton's theorem. In this video, I will show you how to use Norton's theorem with an easy to follow example. By watching carefully, you will learn how to apply Norton's theorem to solve practical problems. Let's get started with solve the problem number 6. Let's consider this network consisting of 5 resistors labeled R1 through R5, as well as one independent voltage source Vs and one independent current source Is. The question now is to find the Norton's equivalent with respect to terminals A and B and terminals B and C. Let's move on to the solution. Let's start first with the Norton's equivalent with respect to terminals A and B. By applying the Norton's theorem between terminals A and B, we can replace this circuit with a current source in parallel with a resistor, which will be denoted as IN and RN. I will start first with the determination of the Norton's resistance. This step can be done by removing all the independent sources in the circuit, which means the voltage source Vs will be replaced by a short circuit and the current source Is will be replaced by an open circuit. The Norton's resistance represents the equivalent resistance between terminals A and B. But first I will consider Ra is the series combination of R1, R2 and R4. That means Ra is equal to R1 plus R2 plus R4, and if we replace the resistors with their numerical values, we obtain Ra is equal to 10 ohms. Rn is equal to the parallel combination of Ra and R3 connected in series with the R5. Therefore, Rn can be calculated using the following formula: Ra times R3 over Ra plus R3 plus R5. And if we replace the resistors with their numerical values, we obtain Rn is equal to 3.857 ohms. After finishing the determination of the Norton's resistance, we proceed to calculate the Norton's current In. The Norton's current is basically the short circuit current calculated between terminals A and B. To find the short circuit current ISC, I will apply the mesh analysis method. It's evident that there are 3 meshes. This is mesh number 1, and this is mesh number 2, and this is mesh number 3. And I will consider IA is the current in mesh 1, and IB is the current in mesh 2, and IC is the current in mesh 3. By applying Kirchhoff's voltage law in mesh 1, we can write R1 times IA minus Vs plus R2 times IA plus R3 times IA minus IC plus R4 times IA minus IB is equal to 0. And if we replace the resistors and the voltage with their numerical values and we continue simplifying this equation, we obtain negative 24 plus 14 times Ia minus 5 times Ib minus 4 times Ic is equal to 0. And in mesh 2, we can see that the current Ib is equal to negative Is. That means Ib is equal to negative 2 amps. Now by applying Kirchhoff's voltage law in mesh 3, we can write R3 times Ic minus Ia plus R5 times IC is equal to 0. If we replace the resistors with their numerical values and we continue simplifying this equation, we obtain negative 4 times IA plus 5 times IC is equal to 0. Now by substituting 2 in 1, we obtain negative 14 plus 14 times IA minus 4 times IC is equal to 0. Now by performing 4 plus 14 over 4 times 1, we derive one equation in terms of IC. That means IC is equal to 14 over 13.5. We get 1.037 amps. And from here we can see that IC is equal to ISC. That means the short circuit current ISC is equal to 1.037 amps. And we know IN is the short circuit current ISC calculated between terminals A and B. That means IN is equal to 1.037 amps. Let's move on now to the Norton's equivalent with respect to terminals B and C. By applying the Norton's theorem between terminals B and C, we can replace this circuit with a current source in parallel with the resistor, which will be denoted as IN and RN. I will start first with the determination of the Norton's resistance Rn. This step can be done by removing all independent sources in the circuit, which means the voltage source Vs will be replaced by a short circuit and the current source Is will be replaced by an open circuit. The Norton's resistance represents the equivalent resistance between terminals B and C. I will consider first Ra is the series combination of R1, R2 and R3. That means Ra is equal to R1 plus R2 plus R3, and if we replace the resistors with their numerical values, we obtain Ra is equal to 9 ohms. Rn is equal to the parallel combination of Ra and R4. Therefore, Rn can be calculated using the following formula: Ra times R4 over Ra plus R4. And if we replace Ra and R4 with their numerical values, we obtain Rn is equal to 3.21 ohms. After finishing the determination of the Norton's resistance, we proceed to calculate the Norton's current In. The Norton's current is basically the short circuit current calculated between terminals B and C. The resistance R4 is short circuited, meaning no current flows through the resistor R4. To find the short circuit current ISC, I'm going to apply Kirchhoff's laws. But first, I will consider this current as current I. Here there is no current flow in this direction because the resistor R3 is short circuit. I will start first by applying Kirchhoff's current law at node 1. We can write ISC is equal to IS minus I. And if we replace IS with its numerical value, we obtain ISC minus 2 minus I is equal to 0. Now by applying Kirchhoff's voltage law in loop 1, we can write R1 times I minus Vs plus R2 times I plus R3 times I is equal to 0. And if we replace the voltage and the resistors with their numerical values and we continue simplifying this equation, we obtain 9 times I minus 24 is equal to 0. From equation 2, we can calculate the current I. I is equal to 24 over 9. We get 2.67 amps. And from equation 1, ISC is equal to 2 plus I. And if we replace I here with its numerical value, we obtain ISC is equal to 4.67 amps. And we know that IN is the short circuit current calculated between terminals B and C. That means IN is equal to 4.67 amps. After completing the calculations, I perform a simulation using SPICE to verify our results. Now let's proceed to the SPICE environment. Here is our networks drawn in SPICE simulator. This is the Norton's equivalent with respect to terminals A and B, and this is Norton's equivalent with respect to terminals B and C. I connected a load resistor between terminals A and B to both the original circuit and the Norton's equivalent circuit. And here also I connect a load resistor between terminals B and C for both the original circuit and Norton equivalent circuit, and then I will simulate their behaviors. Let's move on to analysis, DC analysis, calculate nodal voltage. Let's start first with terminals A and B. We can see here that the current flows through the load resistor is equal to 682.93 milliamps, and here in the Norton's equivalent circuit is equal to 682.89 milliamps. And the voltage across the load resistor is equal to 1.37, and here also 1.37 volt. Let's move on now to the terminals B and C. The current through the load resistor is equal to 2.88 amps, and here also is 2.88 amps. And here the voltage across the load resistor is equal to 5.75 volt, and here is 5.75 volt. Through simulation, we can observe that the two circuits demonstrate identical behavior when connect a load between terminals A and B and C. This outcome confirms the validation of our calculations. Alright, thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video, and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. See you next time in another video about Norton's theorem. Take care and bye bye.